All right. Can everyone in this room take a moment to look at me? And I don't mean any of my teammates or the wall behind me. I mean, focus on me specifically. All right. All right. Now that I have your attention, can everyone take your hands, both your hands, and put them to the side of your eyes like this? And then now use your hands to block out everything so that the only thing you can see is me and nothing else. Now, imagine that your entire life was like this, that the only thing you could see at a time was the thing that you were specifically concentrating on at that moment. All right, look, I know I'm handsome and all, but wouldn't that suck? My good looks aren't enough to be trading away your peripheral vision for, all right? And, all right, well, how about we take that one step further, okay? Say, even when it comes to the thing that you were focusing on, you couldn't even make out every trait of it. Like, let's take a look at the best part of my outfit right now, my beautiful red tie that my roommate let me borrow. All right? What if you couldn't even make out its form and shape? What if you couldn't even tell that it was red? Let's take us even further. What if you couldn't see me at all? What if you were just completely blind? Everything I just mentioned is a possible symptom of retinitis pigmentosa, the most common hereditary disease and the most common hereditary retinal disease, and one that, as of now, has no cure. And curing this disease is exactly what my team and I have been looking into through a field of study called optogenetics.
I'm Natasha Dudek.
I'm Matthew Ganzi.
I'm Michaela Rayo.
I'm Ashi Gupta.
I'm Sarah Warmath.
I'm Rita Vavilov.
My name is Emma Murray.
And I'm Ife Long.
So, with the example that my colleague had presented to you guys, that is the reality of people who have retinitis pigmentosa. Now, the issue with that is, as he said, there is no definitive cure or treatments that we know of right now. To address these issues, our research question is, how can optogenetics be used to advance the treatments in retinitis pigmentosa? It can grant these people with retinitis pigmentosa with normal sight again, and paves the way for a better quality of life for those people, which is what we strive for. It finally increases the availability of treatment through patient and community involvement. But before we get into those topics, we will have to address some background information.
So for those of you who aren't too familiar with optogenetics, let me paint a picture for you. So optogenetics is the combination of the study of light and genetic engineering, and it allows scientists to track and map the activity of different cells in the body. Similar to plant photosynthesis, we have cells in our body that can act as photoreceptors, which means they're sensitive to light, and they can later take that light and harness it into energy. Optogenetics utilizes a protein called opsins, which are delivered to cells using pulses of light or infrared light. And these opsins allow the cells in our body to light up and then be tracked by scientists. This technology is primarily used to track cells and map out their biological mechanisms, but currently optogenetics is being researched for its clinical uses. We decided to focus specifically on retinitis pigmentosa, which my colleague will now tell you more about.
Retinitis pigmentosa, or RP, is a general term for hereditary eye diseases that affect the retina. RP induces mutations in the genes that cause the photoreceptor cells to lose function. Because RP is caused by a variety of different mutations, the onset of the disease varies. Typically, symptoms begin presenting in early childhood and usually affects both eyes. Slowly, the patients will lose their vision as the photoreceptor cells die. Eventually, this will lead to complete blindness.
Yet despite these issues, scientists continue to research possible treatments and cures for retinitis pigmentosa. Currently, optogenetics is the leading therapy in clinical trials worldwide trying to solve this degenerative disease. Utilizing a vector, the crimson R gene is injected into the retina where remaining living photoreceptor cells take the gene, transcribe it, translate it, and produce a protein called rhodopsin. However, the amount of light needed to activate the protein would be too much and toxic to the retina, which is why the injection is partnered with a set of goggles. These goggles utilize an external camera which monitors light intensities and recognizes movement patterns to evoke specific signals. Then the goggles project, quote, transformed pulses of amber light onto the retina in real time, much like a projector onto a theater screen, end quote. From there, all that's left is to teach the patients how to see. Given that the projected visuals aren't natural to the human eye, patients need to understand what they're seeing, so they have to be taught what they're seeing. It's a little time consuming and a lot of effort, but in the end, it's worth it.
So let's move into some of the key issues with our proposal. Since RP is a neurodegenerative disease, there's really no clear timeline for when symptoms will occur. It could be fast or it could be slow. However, if patients were to participate in optogenetic research, it would deem them ineligible for any further optogenetic treatments, regardless of the outcome. This could cause a dilemma for some of the patients. Should patients try optogenetics now and attempt to preserve the vision that they still have left, or should they wait for future and more advanced treatments and risk losing their vision altogether? Patients can also experience something called therapeutic misconceptions, which means that they confuse their role as a subject in a study with the role of a patient receiving a treatment. Optogenetic trials are currently irreversible, and this may be their last chance at treatment. These are just some of the ethical implications that both researchers and RP patients have to consider while considering optogenetics as a potential treatment.
Now, the next question is, when should patients with RP be able to participate in these trials? Symptoms for retinitis pigmentosa begin developing around 10 to 30 years old. If we go through with the study will prevent patients to receive any further treatment for their retinitis pigmentosa. But should we be focusing on the age of these patients or how far into this disorder they're in? If we focus on both, we can get the correct amount of data to research more and the correct consent forms to possibly develop a treatment for retinitis pigmentosa.
To help address some of these key issues, a potential proposition that we can make is the creation of a community advisory board. The creation of this board will allow patients and researchers to work hand in hand, which enables both parties to understand the risks and benefits of the treatment. Along with that, patients could provide real-world insights into what it's like to suffer with the disease, and they could state their priorities given what they want out of the treatment. Moreover, the creation of a strong community could allow the patients to answer some of these ethical dilemmas, because let's face it, as us, people who don't have retinitis pigmentosa, we can't really answer what they need to answer. Together, the efficiency and cost effectiveness of these clinical trials can be used to improve the quality of life of patients suffering from RP.
As of now, there are several groups that support people who deal with this. These groups include the American Academy for Ophthalmology, the Foundation Fighting for Blindness, and the American Council for the Blind. Additionally, doctors and researchers should emphasize on informed consent. Informed consent is the process in which patients are diligently informed of all the potential risks regarding the clinical trial. It is crucial that the patient is given an accurate and coherent description to assure that the patient is fully informed of anything and everything that could go wrong.
Finally, having larger focused trial groups could also be an effective treatment or solution. When scientists work with larger amounts of patients, more data is able to be collected, analyzed, and processed faster. This will allow for researchers to study the effects of their treatment, allowing them to make larger scaled adjustments and leading to an eventual cure.
All right. So the limitations of our proposal is the research funding in the realm of gene therapy. CRISPR, being similar, is $1 to $2 million in research, and that's research overall. And then a closed loop trial around 9,000 for epilepsy, which shows that this is a very expensive proposal. Another limitation of this proposal is having only a few trials done and its influence on participant hesitancy. Not a lot of research into the necessary mechanisms, and participants may have a hard time trusting the research trials in that regard. And finally, one of the other limitations is the current technologies and it's being efficient and effective areas in like cell biology, optics, and tools in general are still limited with this proposal. Which one? Sorry. Oh.
Optogenetics is expanding and will continue to expand for many, many years to come. But with the correct funding, support groups, and consent forms, we can help advance for the treatment of retinitis pigmentosa.
Thank you.
So you guys did a really good job in presenting what I would consider to be a fairly high level, in other words, like 15 to 30,000 foot view of a very specific use of optogenetics to treat a very defined pathology. What I liked about it is its comprehensiveness. So what you did is you said, this is what optogenetics is, this is what the disorder is, this is how it works, and these are what are some capabilities, some limitations, and some possible deconstraints, and then how we go about facilitating those deconstraints. So it made for a very, very nice roadmap. And again, the beauty of a roadmap is that you've got that sort of God's eye view, and you didn't get down too far in the weeds, which I thought was very, very good of you to do, given the fact that this is an ongoing issue. This is not speculative at all. So what you've done is the fancy word is prescind. You've come back and said, let's take a look how this is going, and let's see those paths where it could go correct, where it could go incorrectly. And what we may be able to do is bridge those schisms and gaps, which is perfect. What you really did implicitly was something called gap analysis and correction, right? So it's you identified key areas of gaps, you analyzed why and what the gaps were, and then how might those gaps get corrected, not necessarily at the tactical level, but strategically. So I really commend you on this. The handoffs were great. Everyone presented very, very well and very, very clearly. You were articulate, clear, you went in fast, you hit hard, you got out. Good job. You.
Great presentation. Really enjoyed it. I do want to call out that very dramatic TED Talk quality introduction. Wonderful. Enjoyed that. Yeah, this was a tight and focused presentation on a very real, actual problem. As Dr. Giordano said, it's not speculative. This is real, and I echo the idea of how you well identified gaps that are there. Just as a final point, I like that you brought up the concept of therapeutic misconception. That's a sophisticated ethical concept that you raised, one that's often forgotten and not really even fully understood by people in the research field. Great job.
I also love the introduction. Dr. G had talked about edutainment. This was prime edutainment, and it really did a great job of capturing the audience. And you followed it with something that was clear, that was professional, that was concise, that built exactly like my colleagues have said. I think the only thing I'd add to that I really appreciated was your emphasis on community engagement. So with populations like this, especially with populations where there's dilemmas with recruitment, right? Will getting this technology now possibly cost me an intervention later? Calling out that this is actually something that the community itself should have some agency over and some voice in the research and the progression of the research, given the implications, I thought was a very sophisticated and relevant and timely suggestion. Good job.
Oh, and workable. In other words, you had the list of stakeholders, you justified why they need to come together to the table, and you made the very clear point that you can't really get to informed consent on an individual basis without having an informed community behind them. And then I thought to myself, what if this group just happened to have, oh, I don't know, an audience of stakeholders, how would they explain, oh, you did the presentation precisely needed to get these kinds of stakeholder conversations going? So it came full circle. Very impressive.